Hi, I'm Kemil and this is Chem with Chem. Now in this video, we'll be looking at Forensic Chemistry 101 or Qualitative Analysis. We will be looking at how to identify some metal ions and some anions in solutions, as well as how to identify some common gases. If this is your first time to the channel, I'm recommending that you subscribe, turn on post notifications so you'll be notified the moment new content is added, like the video, and also share the video with someone who you think will find value in it. Let's dive in. Analytical chemists and forensic scientists collect samples from various sites like water systems, sewers, and crime scenes, which they then take back to the lab for analysis. So far, you have learned that the concentration of an analyte in a solution can be determined by doing a series of titrations known as volumetric analysis. An unknown substance may be identified in the lab by qualitative analysis. Qualitative analysis involves identifying the constituents of single substances or mixtures. For the purposes of this video, we will be looking at how to identify the following ions: magnesium 2+ ions, calcium 2+ ions, lead 2+ ions, aluminum 3+ ions, the ammonium ion NH4+, zinc 2+ ions, iron 2+ ion, Fe3+ ions, copper 2+ ions, the carbonate anion CO3 2-, chloride, bromide, iodide, the sulfide anion, the sulfate anion, and the nitrate anion, NO3-. We will also look at how to identify the following gases: ammonia, carbon dioxide, chlorine, hydrogen, oxygen, and sulfur dioxide. Ions are negatively or positively charged species. When an atom or molecule loses negative electrons, a positive ion or a cation is formed. When an atom or molecule gains negative electrons, a negative ion or an anion is formed. Metal ions, also called cations, can be identified using the flame test since each gives a characteristic color. Metallic cations and the ammonium cation can also be identified by the formation and appearance of their hydroxides by adding aqueous sodium hydroxide and aqueous ammonia to solutions containing the ions. This is what we will explore in this video, as well as the test for some common anions and gases mentioned above. The basis on which identifying these cations works is the fact that most hydroxides are insoluble precipitates when formed, except sodium, potassium, and ammonium hydroxide, which form colorless solutions. All hydroxides are insoluble except ammonium hydroxide and those of the alkali metals, that is, the metals in group 1 of the periodic table, including potassium and sodium. This means if sodium hydroxide solution is added to a solution containing any metal ion except ions of the alkali metals, a precipitate will form since the metal ion reacts with the hydroxide ions, forming an insoluble hydroxide. This can be summarized by the general ionic equation shown here. Mn plus is the cation, and we have it interacting with the hydroxide ion, and this will give us our precipitate, M bracket OH bracket. N depends on the valency. So if we have something that's in group 2, we know that N is going to be equal to 2. And we will look at that a little bit further on. Transition metal ions are colored in solutions, and so their precipitates tend to be colored. Most transition metal cations form colored precipitates. The color of the precipitates give the identity of the cation present. It is easy then to identify the transition metal ion that is in solution. It becomes more challenging to identify the cations of groups 2, 3, and 4 metals. So this is the first run. We're going to add a few drops of sodium hydroxide to, and this is our precipitate. We want to pour off most of it. So we add the sodium hydroxide in excess. So pour off some of that so we can add excess. And in excess, our precipitate still persists. So it's a little easy for the transition metal ions, seeing that they form a colored precipitate. So this is our copper 2 plus ions forming a blue gelatinous precipitate. So we want to check. We want to add the base in excess to see if our precipitate will dissolve. And we're seeing that our precipitate is not dissolving. Alright, what we can do to ensure to confirm the presence of copper, we can add a few drops of aqueous ammonia to a fresh sample of our copper 2 plus ions in solution, or the suspected ions, but we know for this we're using controlled ions, controlled solutions. So there we go, and that's our, we get a blue precipitate. We get a blue precipitate. We're just going to pour off most of it so we can check to see if it will be, so we can check to add in excess, and in excess we are seeing where we get our deep blue solution. So this is our copper 2 plus ions in aqueous ammonia. As we saw in that clip, the transition metal ions are colored in aqueous medium and they form colored precipitates which are insoluble in excess aqueous sodium hydroxide and aqueous ammonia, except for copper 2 plus, which dissolves in excess to form a deep blue solution. The challenge is to distinguish among the different metal ions that could form a white precipitate, those cations from groups 2, 3, and 4 metals. And even so, they can still be identified. From the table, magnesium and calcium ions can be distinguished from each other, as though both form white precipitate with aqueous sodium hydroxide, calcium does not form a precipitate with aqueous ammonia. Group 2, 3, and 4 metal ions form white precipitates. Aqueous ammonia would have to be used, and even a further confirmatory test to eventually fully distinguish between all of them. Zinc Zn2 plus, going to add a few drops of sodium hydroxide to our zinc, and as we can see, this is a white precipitate, looks gelatinous, so we're going to pour off
most of it, so we can add. So we can add the sodium hydroxide in excess. So there we're adding excess sodium hydroxide now to the zinc to see if it's soluble. And we're still need to pour off a little more so we can get to add the sodium hydroxide in excess. And there we see our precipitate has dissolved. So we go with the next one, aluminum. We're going to treat it similarly. We're going to add a few drops of aqueous sodium hydroxide, and we're seeing our precipitate emerging. Of course, it's not intense, but we're seeing a white precipitate. So we're going to pour off a little of the aluminum, a little of the substance, so we can now add. So we can add our sodium hydroxide in excess, and we're seeing we're adding the sodium hydroxide in excess is causing our precipitate to, it has caused our precipitate to dissolve. Next one up, calcium. So we're going to bring it forward. A few drops of calcium, sodium hydroxide, and there we go. We're getting a white precipitate. So we're going to pour off most of the mixture so we can attempt to add our sodium hydroxide in excess. And we're seeing where excess sodium hydroxide is present and our precipitate is insoluble. Right? So this takes us to magnesium. We're going to add again a few drops of sodium hydroxide, aqueous sodium hydroxide. We get our precipitate. We're going to pour off most of the mixture so we can add our precipitate, add our sodium hydroxide in excess. And we're seeing where excess sodium hydroxide results, precipitate is still there, did not dissolve. So far we have, from the four, we have two precipitates that remain that have not dissolved. So here we go, the fifth one, we're treating lead, 2+ ions, and we've gotten a white precipitate. So we'll pour off most of it, most of the mixture, so we can add our sodium hydroxide in excess. And let's see. We're still going to pour off some more just to ensure that we add the sodium hydroxide in excess. So there we're seeing that our lead, that precipitate has dissolved in excess sodium hydroxide. So we have, of the 5 ions, we have 3 of them dissolved, the precipitate dissolved. So we'll now have to narrow down
between magnesium and calcium, since both gave a white precipitate which did not dissolve in excess sodium hydroxide just now. So in order to tell which ion is which, whether it's calcium or magnesium, 2+ ions that's present, we would have to subject it to further test. So in this case, we'd have to get a fresh sample of each solution, and we would add to them a small amount of aqueous ammonia and then until in excess. And that is how we would distinguish between our calcium ions and our magnesium ions. Now, we are not expecting a precipitate to be formed with the calcium, and we're expecting a white precipitate to be formed with the magnesium, which would not dissolve in excess ammonia.
Here now, we want to distinguish between calcium ions and the magnesium ions. We just got white precipitate with sodium hydroxide, which did not dissolve. So now we're going to use aqueous ammonia to see if we can distinguish between this calcium ions and the magnesium ions. So we're going to add we're going to start with magnesium, and we're going to add a few drops. We're going to add a few drops of aqueous ammonia to our magnesium ions in solution. And there we're seeing we've gotten a white precipitate. We're now going to pour off most of this precipitate so we can check to see if this precipitate is soluble. We want to check to see if our precipitate is now soluble in excess ammonia, aqueous ammonia. So we're going to add excess aqueous ammonia and check to see if our precipitate is soluble, and we're seeing where our precipitate is insoluble. So that's our magnesium ions. So we'll do the same thing for calcium ions. We'll do the same thing for calcium ions. So we're going to add a few drops of aqueous ammonia, and we are not seeing any precipitate. We're not seeing any precipitate being formed. So that's what we use to distinguish between the two. We don't get any precipitate with our aqueous ammonia. We barely get any precipitate with aqueous ammonia.
So we were just able to use aqueous ammonia to distinguish between calcium and magnesium ions. We got no precipitate with calcium, and we got a white precipitate with magnesium, which did not dissolve in excess. Now, to distinguish among aluminum ions, lead ions, and zinc ions, we would also have to subject the three samples to further testing. Would have to use a few drops of aqueous ammonia, which would give us a white precipitate with each of them, and the precipitate for zinc would actually dissolve. That would now leave us with the aluminum and lead ions for us to distinguish between, and we would have to go ahead now and do the confirmatory test that is outlined at the bottom of the table to distinguish between Al3 plus and Pb2 plus, lead 2 plus ions. And in this case, we would add aqueous potassium iodide, and we expect the lead ions to give us a yellow precipitate, and we do not expect any precipitate to be formed with our Al3 plus ions.
We're trying to distinguish between aluminum and zinc, seeing that both of them give us a white precipitate. So we're going to start with fresh samples of our aluminum, and we're going to add a small amount of potassium iodide to see if we can distinguish between. Okay, now we've added more than a small amount and we don't see anything happening. So we put that back in the testing rack, and we're going to take our lead 2 plus ions, right? And we're going to add a small amount of potassium iodide. Again, potassium iodide equals potassium iodide. We're going to add a small amount to our and there we go. This is more than a small amount. We have our, we call this a bright yellow precipitate being formed. So there we have it. Confirmatory test. We've separated, or we've distinguished between our lead ions, our Pb2 plus ions, and our Al3 plus ions. There we have it.
So this now takes us to our test for anions in solutions. We'll start with the halides. Now, the reagents that we use to test for the halides, chloride, bromide, iodide, are silver nitrate followed by aqueous ammonia. And the idea here is that if any of the halide ions are present, then they will form a precipitate with the silver nitrate. So all nitrates are soluble. So we would expect Ag plus aqueous ions to be in solution if we're using silver nitrate. Now, all halides are soluble except lead and silver. So the idea, as I said just now, is that if any of the halide ions are present, then they would precipitate out of solution, and the color of the precipitate would tell us which of the halide ions we have present. So this is just an equation that we could use to represent if we have chloride present. So we would have Ag Ag plus aqueous ions from the silver nitrate. And if whatever we're testing, the substance we're testing contains chloride ions, then we would expect to see a white precipitate formed. And that white precipitate would represent silver chloride. And then when aqueous ammonia is added, then this precipitate would dissolve in aqueous ammonia. Now, in similar manner, if we have or if we had bromide present, then we would expect this time a cream precipitate following the same principle. The aqueous silver ions precipitating out of solution to give us silver bromide. And it follows in the same manner. If we added silver nitrate and iodide is present, we would get a yellow precipitate. We have to note that the precipitate for silver bromide is cream and it is slightly soluble in excess ammonia. The precipitate for silver iodide is yellow and it does not dissolve in aqueous ammonia. So that is pretty much it for the test for our halides. Silver nitrate followed by aqueous ammonia. That's it. Now, there's a test that is used to distinguish between or to distinguish among the carbonate, the sulfite, and the sulfate ions. And this one is barium ions, aqueous barium ions, which would be administered either in the form of barium chloride or barium nitrate. So we know all nitrates are soluble. So these two reagents would contain aqueous barium ions, aqueous Ba2 plus ions. And the principle here is that these aqueous barium ions would be forming a precipitate with either the carbonate, the sulfite, or the sulfate. Now, to distinguish among the three, we would have to now add dilute acid to see if the precipitate would dissolve. Upon dissolving, if it dissolves, we would now test the gas that is evolved. So if we get a white precipitate to begin with, then it means that either carbonate, the sulfite, or the sulfate anion would be present. And then if the precipitate dissolves, given effervescence and that gas is collected, effervescence speaks to the presence or the evolution of a gas. So if we collect this gas and we bubble it in lime water, that's calcium hydroxide, and a white precipitate is formed, then it would give rise to the presence of carbon dioxide. Now, if we have a sulfide present, then the gas that's given off when the white precipitate dissolves, that gas, if bubbled through acidified potassium manganate 7 solution, would actually cause it to change from purple to colorless, which is telling us that SO2 sulfur dioxide is present, which is a reducing agent. Now, if our white precipitate does not dissolve in dilute acid, then it's telling us that we have barium sulfate present, or we have the sulfate ions present. And this equation would be representing the ionic equation for if we have sulfate present. So it would be the barium Ba2 plus ions combining with the sulfate ions, SO42 minus ions, which are aqueous, and those would come together to give us our precipitate, our white precipitate, barium sulfate. Now, our nitrate would not give us any precipitate here. To test for nitrate, we would have to add copper followed by concentrated sulfuric acid, and this would give us what we call a brown ring, which is telling us that NO2, nitrogen dioxide, is present. We could also add aluminum powder and heat the solution, the mixture, and we would get ammonia being given off. But of course, the way to identify ammonia would be to use moist red litmus. And if ammonia is present, then it would turn it blue because ammonia is the only alkaline gas. Now, on that note of gas, we will just look at how to test for the common gases that were mentioned earlier. So, ammonia is the only alkaline gas, so it will turn damp red litmus to blue. Carbon dioxide will give a white precipitate with lime water. And lime water here is calcium hydroxide. Don't want persons to think that lime water has anything to do with squeezing lime in water, right? So this precipitate would dissolve as more carbon dioxide or more gas is added. Now, chlorine bleaches litmus paper, so it will turn blue litmus paper to red, but it will also go a step further by bleaching it. Hydrogen puts out a lighted splint with a pop, which tells us that it's explosive. Oxygen, it relights a glowing splint, and sulfur dioxide turns acidified aqueous potassium manganate 7 from purple to colorless. That's what we would use to identify the presence of sulfur dioxide. It is a reducing agent. And we've come to the end of this session on Forensic Chemistry 101 or qualitative analysis. If you like the content, if you found this helpful, I'm asking you to subscribe if you haven't done so, like the video, and also share it with someone with whom you think would find value in it. Thank you for joining us. See you in the next video.